Hello, everyone. I'm sorry, it looks like we're having some technical difficulties. Um, Ramsey hasn't been able to log in and no one else, as a matter of fact. I'm not sure what's happening. So we might have to reschedule this. I'll keep playing with this for a couple minutes and see if I can figure it out, but my apologies for it not working. I'm not sure what's happening.
Hi.
Hello, Ramsey. Hello, Ramsey. Hello, Ramsey. Hello again, Ramsey. Can't hear you. Joaquin, can you hear Ramsey and I, or did Ramsey try there's a microphone button at the very top, or a sort of like a little settings wheel. Maybe it's chosen the wrong microphone. Aha! I heard something.
How about that? Hello?
Great.
Yes, no, maybe?
Yeah, I hear you now. Okay, perfect.
Yeah, you were right. It was in the settings it selected a different mic. Sorry about that.
Okay, no problem. Yeah, sorry, I'm not sure what's happening with the link. Why it wasn't working. This is I wonder if it would have something to do with the date. Maybe I had it. I was in Europe when I configured it, so maybe that confused it a little bit.
Right. Yeah, it's not. Yeah, it's all right. I mean, yeah. Do you want me to kind of start with what I've got and share it with you, and then I guess you can talk as we go along. Really, that's probably easier.
Yeah. Okay. So you have slides you're going to show? Yeah.
Yeah, I've got some slides I can show. It's probably the better way to talk through it, I guess.
Okay. All right.
Watching it later on, it can make sense.
Sounds good. Well, so let's get started. So thank you everyone for joining us. Sorry for the delay. So I'd like to welcome Ramsey Selim from Kaiam Corporation. So Ramsey took this course with us on the very first version of this, and I was very pleased to find out he's taking this course because he has a lot of experience in designing various types of transceiver products, and he has much more experience than just silicon photonics. He's also worked with indium phosphide and silica. And he's working for a company that's putting all these pieces together, including some electronics, I understand, to make a transceiver. And these transceivers are going to be used in the data centers like the Googles and the Facebooks and things of the world. So I'm very excited that he's offered to share with us what he's working on. And thanks for joining, Selim. So floor is yours.
Thank you very much. Can you tell me a bit about what this course is like this round?
Pretty similar.
Mm-hmm. Okay, yeah. Let's see, is there a share screen button here?
Yeah, it's on the far left. There's a little green.
Oh, yeah, got it. There we go. Oh.
Good.
Right. Thank you for the introduction. I'm, like Lucas was saying, I'm Ramsey Selim, working for Kaiam, and I was hoping to kind of talk about the transceivers in the datacom market, and hopefully do a little focus on silicon photonics transceivers to fit in with what is going on at the course. When I was doing the course, there was a lot of passive silicon photonics, doing some kind of laying out of the Y splitters and grating couplers, and maybe kind of fancy Mach-Zehnder interferometers and the like. So yeah, this is kind of some applications of using these, and so the presentation itself is kind of split into two parts. So part one, kind of give the Kaiam overview, who we are, introduce that to folk, do an overview of the datacoms market, well, datacoms generally, and then the transceiver market a bit more specifically.
Hey Selim, by the way, the screen that we're seeing is your PowerPoint presentation, but it's not full screen.
Oh.
Is that intentional, or is it?
That's not intentional. That's thank you for bringing that to my attention. Let me see where.
Maybe you have two monitors and it's displaying on a different one.
No, it's... Yeah, it doesn't seem to have it in full screen, does it?
Maybe F5?
Well, it's on full screen when I see it. Like, so right now for me it's on full screen, but for you it's not, is it?
Oh, are you sharing, when you chose share, did you choose share screen or did you share presentation maybe? Or?
Oh, I said share presentation. Maybe I should say share screen. Let me try it again, sorry. Let's stop that.
That seems to be... Oh, hello, I see you again.
Hey, yeah. Okay, so full screen, start. So now I should be sharing the screen.
Yeah, perfect.
How about
Great.
that?
Fantastic.
Yeah, okay. Sorry about that. So the content, like I say, is split into two. One is an overview, Kaiam, the datacoms, why there's a push for more and faster, and why we do the business that we're doing and the development we're doing. And then I'll look at transceiver market and give a quick overview over that. And then what I'll try to do is go into a bit more of a technical focus on the Silicon Photonics transceiver. So Kaiam, we have one of our products uses or leverages the Silicon Photonics technology, and we're hoping to maybe kind of give that a bit more of an example there. And then finally a summary. So Kaiam, we're a startup, Silicon Valley startup in 2009. The same group of people that were the core of the startup of Santer, kind of maybe over 15 years ago now, or 10 years ago now. That so Santer are responsible for, their tunable lasers are responsible for driving 2/3 of the internet. So the same core group decided to start up Kaiam, and the idea being using hybrids and leveraging MEMS technology, and the hybrids being playing on the silica, silicon, indium phosphide monolithics, aims to kind of leverage the best of each platform using MEMS technology to align them. 2013, the Kaiam US purchased or acquired a design and manufacturing warehouse in Scotland, which were called Gemfire, and now it's one with two sites. You've got Kaiam USA, Kaiam UK. In fact, I'm based in Kaiam UK, so I've joined recently. 2015, there was the move from prototyping and giving samples to actually now high volume production of what we call 40G, TOSA, ROSA, and I'll go into them a bit more detail as the presentation goes on. 2016, so this year, we've even moved from 40G to 100G transceivers or transmitters and receivers for the internet, and that's on multiple products, Silicon Photonics being one of them. Other types we have, one we call the chip on board, but that's just there as an example. We also did the first kind of worldwide demo for a Silicon Photonics transceiver at OFC, which is one of the telecoms conferences, probably one of the larger ones, and that was earlier in March of this year. So kind of datacom overview, and really what is driving the market and why go faster. Really there's the Web 2.0 and what we call the Internet of Things, and the Web 2.0 being social media. So whenever you take a selfie or upload a video to YouTube, or share a funny cat video, that kind of stuff, that's all Web 2.0 really, and that's increasing so much because the users now have direct access on their phones, on their tablets, on their TVs. There's just so much accessibility as well to loading and uploading new data to the internet, and then the Internet of Things is more of machine to machine That's mainly kind of the Internet of Things. So if you've got the Apple car or the Google car, and after that you go to automated cars and driving, then cars talk to each other, that's machine to machine. And then there's more, maybe less of a clear example, but a more practical one is servers talking to each other as well and communicating with each other. But yeah, so that's the drive for more usage and the internet kind of growing so quickly. But also we've moved from putting things on servers to or remote or housed servers to remote cloud and remote servers and data centers. So companies now will save their data somewhere else, not in-house. So Netflix, for example, they won't have in-house servers. It will be not necessarily offshore, but with somebody else. And so Google and the likes, they all have these big data centers as well, and the data centers are having to get bigger because they're hosting more information. And as the data centers get bigger, they can't use the normal multi-mode fiber anymore because that can't reach as far. So they're having to move to single-mode fiber, which means to get more channels, you're going to need more single-mode fiber, or more lanes, sorry. And then also things like you've got the traffic between each other. So when you hit a search on Google, your the result you get back, so you get a list of results, thousands of results, that's only like 1 in 1,000 of the machine-to-machine conversation or traffic that the Google servers are having. So the Google servers have an immense search going on between the servers, and then they give you back, I don't know, 1,000 results or something. So that kind of accounts for a lot of the data as well that's going on. And there's some other kind of programs in trying to make that more intelligent through software, so that it's not doing so much intensive searches through servers, but it's a bit more intelligent. But yeah, but our side is more really hardware, really. So like with the datacom, you can see the data centers are increasing. So here there's a few examples I just kind of got off as well from the internet, really. So the Apple, the Google, etc. And then inside the data center itself, you see just rows and rows of servers. But these servers, to connect to the internet, they need an interface. And this is where Kaiam starts to come in, really. So the interface it needs, at the top of each of these servers is a switch. So I've kind of given a wee example here, really, just a rough thing. Up on top of the server, you've got a switch, and then the switch is mainly 2 parts. The electronics that's interfacing with the server, and then you've got the optics that needs to interface with the fiber that's coming into the server. So when you hit search on Google from home, it goes to your fiber to home, goes across the fiber to the servers, and when it gets to the server, it connects to our transceivers or somebody else's transceivers. So 2 transceivers themselves, and then these transceivers translate that optics to something the switch can understand, then to something the server can understand, and vice versa. So the transceiver market itself, there's lots of different ways of doing it. The main way that people have done it in the past, have made them, is kind of aligning bulk optics, and you get like rows of people just putting in bits of optics to align them together to get the transmitters and receivers set up. But there are more intelligent ways as well of doing it, perhaps, going forward. So there's the Silicon Photonics, and like I was saying, for example, Kaiam have kind of championed that, but also Applied Micro have demoed one as well themselves. There are other platforms like indium phosphide, Effect Photonics, they've got 100G transceiver in that using indium phosphide integration. But as you can see, there's a lot of different solutions, and in fact, Kaiam itself, we have so many. And the reason I'm putting this here is to kind of highlight that actually there's lots of different products, and the reason behind that is that companies want their own thing. There isn't a clear standard. So here, for example, you see in 2014 to 2015, there was far reach, 10-kilometer reach, there's 2K reach, there was multi-mode, there was single mode. 2016, you'd think it would narrow down to less samples, but actually there's new variants again. And in fact, in 2016, you can see here the Silicon Photonics one on here now. But the drivers for this, or the people that own the clouds or own the servers and the data centers, are the Facebook, the Google, the Microsoft, these guys. They've got their own targets, their own way of doing things as well. So Facebook, for example, they've put out the challenge for, we want $1 per gigabit per second for the transceivers, which at the moment would be a really tricky, difficult challenge, because they're more than 3 to 9 times that cost, in a sense. Google would say, well, actually, they don't want to standardize. One of the comments we were saying was actually life's too short to wait for standardization, they were saying. And then Microsoft backing that up by saying, actually, there's enough big companies that have enough money behind them to champion their own solution. So that's why there's so many different technologies and different targets, because each one does their own thing. So we've got the Silicon Photonics itself, and I'll kind of take that one in to kind of look at it as an example of what we're actually doing. So here, this is what the people we work with. So let me kind of, maybe I should wind back a bit, or yeah. Our Silicon Photonics transceiver, I was going to explain that in a few more slides, but maybe it's better to explain it first. Let me jump ahead and I'll come back to these slides. So our Silicon Photonics transceiver has multiple sections in it. So you have the, yeah, here's probably better. So you've got a section that has lasers and your so it's generating the light, and then it goes to column 2 here, where you've got the silicon, for example, and it does the modulation, or the if you're transmitting, and then it goes to a multiplexer to get all these lines into one line to get to put it onto the fiber. And then on the receiver side, it's the other way around. So the fibers come into the demultiplexer, so it's demultiplexing these channels and put them into their own lines for the photo detectors to pick up and then go to the electronics. So Silicon Photonics can do a single one, and that has been published before. So that was the example I was showing here, where they've kind of shown, actually they can have a laser source, put it to so that's in the green at the bottom left. They can connect that to a grating coupler that you would have, something similar to what you would have done on this course. And here you break it into channels, so channel 1, 2, 3, or 4, and that would get sent to what's in the pinkish square, and that would be the electro-optics. So you've got the modulator there, for example, the high-speed phase modulation, and so that wouldn't be a passive device, but a similar thing of interferometry would be the MZI and a passive device, similar in the sense of the optics, not the electro-optics. And then after that, you'd interface to the output through a grating coupler. So you can see the top side there, that's the transmitter, and at the bottom section here you've got the receiver, and you've got a slightly different grating coupler coming from the optics on the right hand side, where you've got a two polarizations coming in. So you've got your TE and your TM, and actually this one's splitting these two using their polarization splitting grating coupler, and then to the receiver, and finally to the PDs. But yeah, so what Kaiam have done is we've gone and said, well, actually, we find that we can probably source the laser and align it to the Silicon Photonics for cheaper, because we champion, if you remember, hybrids. So we went and got the laser from somewhere else, and got the Silicon Photonics from these guys. So here you can see, so you've got the laser, we're sourcing them, and then we're sourcing the Silicon Photonics itself, where the silicon is really good at doing the modulation, the photo detection, so let's use that platform for that. And then the glass, or the silicon oxide, is really good at being tuned and used for mux and demux. So we've used that platform, and we've used the MEMS technology to align these things to each other, especially on the laser side and the so that's kind of covered some of this here as well. In terms of why are we doing that, really, is because for us we're finding that actually it's more cost effective for us at the moment to make things on PLC for silica for multiplexing and demultiplexing, because we haven't found a solution, a proper solution for us yet to make that in silicon. However, silicon, and then silicon for light generation is probably not the best option yet. So that again, indium phosphide, using that for that. But silicon photonics is really good for us to drive the price down. So if we want to meet that Facebook target of $1 per gigabit per second, silicon photonics is the option. That's the way to go to drive that cost down, really. So that's why we're investing in it. We're investing and we're backing it as well. So I'll kind of take that in a bit more and look at the what the photonics itself, the silicon photonics, look like. Now we've sourced these, so I can kind of comment on them more than actually maybe perhaps explain them. But what we were finding is that so we're using kind of rib waveguides at the 1310 central wavelength. And we're looking at kind of losses. We were seeing losses of, to be fair, less than 1.9 dB per centimeter of propagation loss. In fact, I think in the summary I find that it's probably much lower than that as well. So we're targeting 1300 here, 1310. You can see here also the dimensions of the waveguide, 320 nanometer by really 300 nanometer. I think it's a bit more than that. And then we've got the couplers themselves. So the grating couplers themselves. Like I said, there's a single polarization grating couplers, so the one on the left, where that's just dealing with TE for us. And then you've got, and that's for the transmitters. And then the receiver side, there are polarization splitting grating couplers that are separating the TE and the TM into two different waveguides. And again, the loss here, so for the polarization splitter, it will be higher than the single polarization. So you get here, we get 3.25 and 2.2. Maybe a bit lower than that in the final thing as we've started to produce it now in higher volume. It's a bit lower than that now. And then the modulator, what we're using here is a 4 to 6 dB per centimeter insertion was what we're seeing. Probably, I think it's like 2.5 volt deep high. And then the photodiodes that we're using here are 1 milliampere responsivity with a dark current of 100 nanoampere. Let's see here, I've got any more kind of personal comments on that on my notes that might be helpful. I think they're driven at 50, yeah, they operate at about 50 degrees, these PDs. And the modulators we're finding actually are about 0.55, I've got my personal notes here, dB, I think, what is it here, 0.55, no, per millimeter, sorry, yeah, this is per centimeter, that makes more sense. So in between 4 and 6, yeah, it's about 5, that's about right. So as a whole unit for us, what we're finding is that our transceiver, you've got different sections. So the fiber to the glass or to the PLC, the silica, we're finding losses of about 0.4 dB per facet as we kind of interface between that. And then from there it goes through the PLC waveguides, the mux, and there's a combined loss there of about 4.5 from the muxing or demuxing and the propagation loss. And then the interface between the silicon photonics and the PLC, So it's a bit lower than the 1.9 that I reported earlier on in the presentation. I think our latest measurements are closer to 1 dB. Oh, that's propagation loss, sorry, yeah. And then, yeah, 1.6 dB per grating coupler. So 1 dB per centimeter for propagation loss and 1.6 per grating coupler, which I think is pretty good. It's not that bad. We're also looking at some development for this, because one of the key things for us is actually, because we're not making the silicon photonics, we're trying to think about how can we make the interface between the silicon photonics and the PLC or the silica better, lower loss, so that the more we can reduce the loss, the better. Can we reduce that through edge coupling, for example, as opposed to grating couplers? And that's kind of been ongoing thinking about that, and some experiments happening at the moment. I think we've sent some stuff to get made just to test it out. So yeah, the development work that's going on in this, there's, like I say, so 0.34 down there is the input-output with the dependency of the grating couplers is an issue for us, so that's why we're looking at edge couplers as another option. Can we tune the silicon? That would be great. I think there seems to be a lot of breakthroughs recently that are getting closer and closer to this through permanent thermal tuning, but we haven't seen like clear breakthroughs yet. But that would be great to be able to transition the multiplexing, demultiplexing to the silicon platform, and then that would help us reduce the cost even further, so that we can meet the targets of the Facebook and the Google and the Twitter and these people. But yeah, so these kind of the main things. I guess the more we go to wafer scale integration, like Intel are doing, that's the kind of way to go really in terms of reducing that cost even further, really. I think that was the last thing on this. No, that's a bit of a summary here. So, like I say, there's quite a lot going on the market side of it, and we think that silicon photonics is the way to go, really, in terms of our hybrid technology. The more we can leverage of silicon photonics, the better, because it's a cheaper product and more integratable. And we've got a lot of experience in aligning these things to each other and packaging them quite quickly, and getting the interconnects out. And our partners are some of the best in the world, if not the technology leaders in their field themselves, so that kind of enables us. But yeah, so that's kind of a quick summary of what's been going on here. It's probably better to kind of open the floor for questions so that we can go into this a bit deeper.
Great, thanks, Ramsey. So I think there's a lot of people who are watching this on the course webpage, and
yeah.
So if people have questions, you can post them in the discussion, or you can type them in onto the Google Hangouts webpage if you have access to that. So okay, so I don't see any questions yet. So
yeah, it's fine. I'll just kind of remove the sharing presentation.
But you might want to keep your slides up. There might be some. Well, that's okay.
Yeah. Okay.
I'll start with the first question. So the library that you have, so you have grading couplers and things like that. Was everything provided to you by the foundry, or did you guys have to develop your own components as well?
It was a two-way conversation. So they had stuff that they had optimized and done a lot of development work in it, and we had previously looked at what we would think works better with our PLC, but also it helps us look at how we can interface our PLC to be better for their grating couplers. So yeah, it was a two-way conversation. We put an input to it as well, saying actually we think this will work better. But yeah, so we've done some development. But what can I say on that? It was mainly on the input-output interface, not much on the chip itself.
Okay, so that means the modulators and the detectors and things, they had a pretty mature list of components already that you can build on, right?
Yeah, they've had some stuff out for a couple of years now, I think. So we kind of met them at the right time, where they were kind of just starting to introduce their technology to the industry, and we were looking at moving to Silicon Photonics with our technology, really. But yeah, so they do have their modulators pretty mature, their photodetectors.
Mm-hmm. Did you mention the name of the foundry? Probably not, right?
I'm not allowed to in terms of this is recorded.
Sure.
Anything that's recorded, I can't really. But yeah, so it's one of the leading European foundries in that sense. There's only like less than a handful of them.
Mm-hmm. Great. Okay. Question about your PLCs. So you're coupling PLCs. Ones I've seen before usually are edge coupled, and so you guys did some work to have your PLCs have grading couplers on them, and then you use another grading coupler to on the silicon photonic chip. So can you describe that interface?
Yeah, so I've used a what we call like a flip chip technology. So there's also kind of flavors of it. So we have tried edge coupling as well, and the edge coupling does work as well. To be fair with us, I mean we haven't ruled out one of them. I can't say in terms of we do use the two options in terms of what we're making, because there's not a clear differentiator for us at the moment still with them. But it is great in couplers in terms of flip chipping. But I can try to see if I can find some more notes on that. Is my screen still shared here? I can't really tell. So
no, like we can see your face right now.
Oh, okay. Right. I'm just going to figure out. See if I can do it. Yeah, I don't think I haven't got I'm using my personal computer here, so I haven't got the extra notes on it, so I can't really elaborate on it, unfortunately.
No problem.
Yeah, but I can probably send you something, and then you can add it to the questions at the end for people that are kind of looking at it in the comments or something.
Great. Okay, so another question on. So you mentioned you're putting the filtering on the PLC chip rather than the silicon photonic chip, and the reason there was partly manufacturing variability and partly because of thermal variations, and so that you would need to temperature control it. So so then I'm wondering when you mentioned there's nothing great out there for silicon photonics in terms of thermal management. Are you interested in a solution that is athermal, namely where the device does not change with temperature, or are you interested in a solution that can be electronically controlled and stabilized with feedback loops?
Well, for this specific one, actually, well, we're interested in both, but let me kind of unpack that. So when I was saying tuning, what I was kind of leading to, or trying to lead to, maybe I kind of misphrased it, but our AWGs are made on array wave gratings that do the multiplexing, demultiplexing, are made on the silicon oxide PLC, and that we can tune if we have to, which usually with AWGs you do need to, whereas we haven't found a good way of doing that on silicon yet. But the two applications do exist other than transceivers themselves. So we do other things here that would require changing with temperature. So athermal and thermal would both be things for silicon that we'd be quite interested in, actually. Is that kind of answer your question?
Your requirement is to be able to tune it so that you can match the wavelength of the lasers. Is that what you mean?
Exactly. Yeah. Exactly.
So what's the issues with the filters on silicon? Tuning them doesn't seem to be too complicated. So I don't understand what the limitation is.
Well, so I guess when we tune to create an AWG that on silicon and tune that AWG for high volume manufacturing, you would the variability on the silicon is still quite wide in comparison to the tolerance you can get by not tuning it. So if you don't tune the silicon and you create an AWG, the results so far are still kind of quite variable, whereas so your channels aren't really filtered out on a high production level, at least from what I've been seeing. Maybe I've kind of missed out on it. Is there something that you know of that would be useful?
Well, I guess at UBC, as an example, we've been working on a variety of filters based, I guess the ones that I've been most excited about are based on contradirectional grading couplers. So those are the two waveguides with Bragg gratings on them. Very Bragg grating filters. But then you can, I guess in general, you can do thermal tuning. I mean, I agree with you about the AWG challenges because you have numerous waveguides and there's variability among those waveguides. And so how do you heat those? You have a collection of waveguides, and if you can heat the whole thing, but then that might not work so well. So.
Yeah, I mean, we're trying not to, well, we would prefer to be able to do, for our products, to keep them cheap and small, because energy is a key factor as well, and the heat consumption, or the heat dissipation is quite big as well, is to not have heaters that are on there that we need. So it would be a one-off tuning, and that's done. So it's a permanent tune in a sense. So the silica AWGs can be tuned once, and that's it. They're tuned to the channel we want, or to the channels we want. Whereas the silicon, my understanding is that they would need continuous thermal tuning. Am I correct in that? In my understanding of that?
Well, yeah, definitely the silicon ones definitely need to be continuously heated. Yeah. Now, did you say the glass ones? You just you bake them once and then that's it, and they stay.
Yeah, well, they don't. No, well, they don't get thermally tuned. They will be UV trimmed.
I see. Okay, so you guys do trimming to get them to the right wavelength. Okay, that makes sense. Okay, so you get your filter made perfectly to what you need. Okay, so that's a trimming. Okay, I understand.
Yeah, exactly. So yeah, I think once we can do that on silicon, there will be a big shift towards a big silicon chip as well.
Yeah, there's been some research on trimming, and my impression is that that not too many people are interested in trimming on silicon, but rather doing electronic control, so using various types of heaters and so on to stabilize to create loops. You know, so for example, ring resonators are very popular, at least in the research community, and so then the ring resonator could lock on to the wavelength of your laser.
All right, I see. Because I saw at the conference in March, the OFC conference, there was one, I think, presentation about permanently tuning, thermally tuning silicon, but it still seemed quite adventurous in a sense. They were still trying it out, to be fair, but they had some decent results to start for a starting research.
Yeah, the question is how mass manufacturable that's going to be. I'm not
yeah,
sure.
for us it's still quite early. Yeah.
Yeah, like you can do things like with various types of etching, localized etching, or AFM writing, or FIB writing, or laser writing, things like that on top of it. But that's an individual device trimming kind of thing. So.
Right. Yeah.
Okay. So what about the insertion loss of your AWG the MUX DMUX AWG? Is that a concern from a product perspective? Because I guess when you're going in and out, you're losing in total 8.8 dB, which seems like almost 10% of the power. That seems like a lot.
Yeah. I think because everything else is not losing much, it's the PLC that's as low as we can get it really so far. I mean, we're looking at trying to reduce that even further, but probably our main bottleneck with the PLC, as opposed to insertion loss, would be footprint. where obviously silicon is, you can't really compare it, it's so much smaller. But the loss itself, I think we kind of manage because we know what to expect from our AWGs. It will always be the same, and it's something we're quite familiar with and we can work with. If we can reduce that, it would be great. But already the propagation loss per trip, I think, is about 0.1 dB, so that's quite low. But the muxing and demuxing, because you've got several channels on there as well, there's already some loss in itself.
Mm-hmm.
Yeah,
that'd be great. Yeah, it's quite a loss. I mean, if you think about how much extra laser power, if you need an extra 8.8 dB of laser power, how many picojoules per bit does that add to your link budget? It's probably quite a bit.
Yeah, if you've got some ideas on there, that would be pretty cool for us.
Yeah. Well, there's I guess there's quite a lot of people working on various multiplexing and filter technologies in silicon, but I think it sounds like there's pros and cons. Like you said, you were able to trim your PLC. I guess that's a nice advantage, which maybe is not as easy to do in silicon. So.
Yeah, that's our key thing, really. That's probably the main thing, main reason behind sticking to PLC for the AWGs at the moment, but trying to keep tabs on where silicon is going in that, because that would be a really good shift in terms of energy, size, etc.
Mm-hmm.
Yeah. Especially the footprint, I think, again, is quite a big thing for us, because the PLC is quite big in comparison. But yeah.
Okay, I'm just looking to see if there's any other questions. Okay, I'm not seeing any more questions.
That's fine.
Okay.
Why do you have nitride on top of the RIP waveguide?
On the silicon or silica? Where are we talking?
On the silicon.
Let me just bring it back up one second. So where did you see this? Was this in the waveguide slide?
Yeah, in the waveguide slide, yeah, in your cross section, your rib waveguide.
Yeah. Can you see the slide, or shall I try to share that one also? Can you see the slide now?
Not yet, no.
Yeah. Let's share this one. How about now?
Yes, that's fine.
Yeah. All right. I think this is where you're talking about. That. So why is there silicon nitride on top of the silicon? That's a good question. I think that's probably one for Lucas to answer, really, not me. Maybe Lucas, you'd be able to answer that.
Wow. Well, without knowing what the foundry and what else are the things, I'm not sure if I can actually, to be honest.
Well, let me have a think then. What here? So silicon nitride in comparison to the silica.
I mean, I guess it's. I mean, you know, there's a couple uses. I could see this being useful for a waveguiding layer potentially. So you might be doing multiple waveguiding layers. So you could implement your AWG using that silicon nitride layer, if you wanted to. I've seen some people doing that. Another possibility is that the silicon nitride is used for the grating couplers to try to improve the insertion loss. I'm not sure if that's what it's being used for.
Yeah, I think it's for the insertion loss, to be honest, but I'm not entirely sure. Is why I've referred to you, Lucas, because I'm not entirely sure, really. Yeah, I don't know why they use it, to be honest. Good question. Very good question. I mean, silicon nitride for PLC, what we would use it is to reduce the size of the PLC, so to reduce the bend radii, because it's got a high index in comparison. But using it, so here you've got a high index running through the silica here in the middle, and it's what, 320? No, that's the width of the guide. Yeah, I'm not entirely sure. I can't comment further, to be honest.
Okay.
Thank you.
It's a good question. Asking them later the same question. Why are you using silicon nitride here?
Yep. Yeah. Let us know if you have any ideas. Yeah, it might be for the grading coupler. I've seen people do this for grading couplers to improve the insertion loss. So that could be that. So especially if you don't have a bottom DBR on the bottom, then this one on top could be helping. Okay.
One thing we find actually is that it'd be good to get your input really, Lucas, as well here, is that we're kind of looking or exploring moving from grating couplers to edge coupling. So you did ask earlier on about the coupling that we're using, and one of the things is the amount of loss that you get from just the light that's propagating vertically down beyond the waveguide. Let me see if there's one here I can get so I can maybe show a bit more. Yeah, grating couplers here. So if you think of for example, fiber, for example, shining down directly onto that grating coupler, there's a lot of light that just goes down to the bottom that is lost in a sense. There have been tricks where people try to get that light reflected back up, so that all your light, or the maximum, is going through to the right there to kind of get caught and propagate. But we still find there's a substantial amount that's in there that is lost, and we're thinking of moving to some other techniques of edge coupling. But I recall when I was on the Silicon Photonics course that I think you, Lucas, a champion at the time of the grating couplers. If I remember, there was a interview with the guys that were doing the E-beam. I think it was in DC, was it maybe? Washington or something? And they were talking about how some of their customers did use edge coupling, in fact, because for them it was just as good. He didn't say better, but he did say just as good, or something down that line. And I wondered if you had any comments on it.
Yeah, I think the field is split right now in terms of edge coupling and grating coupler. I would say right now they have similar performance. The edge couplers have the advantage of a more broadband operation in terms of wavelength response. So that's one. So really there's pros and cons. I mean, the fact that you have it working so well right now, it makes it harder for you to justify switching technologies if this is already working well. It seems like there's other places where you might be able to optimize further, like the MUX and DMUX, but
yeah.
So I would say right now there's no, there's not like one is clearly the winner over the other. I mean, Luxtera has had a product using grating couplers for many years, and then you guys have one now as well, and then there's other companies doing edge coupling. So I think they're both valid approaches. So I mean, the world's best grating couplers these days, I think the world's best demonstration is somewhere below half a dB insertion loss with a variety of tricks, like you said, some of the mirrors, multi-layer as well. Some people are doing so. Yeah,
there's been a lot of things. We've worked with different foundries in Europe to just developing them ourselves, just to test against our PLC, just to see if we can optimize them. And that's where we're checking the grating couplers versus the edge couplers. Variants on them that I couldn't really include in this presentation, unfortunately. But we found it quite interesting to see that actually different foundries do it substantially differently. They do their grating couplers quite differently, and hence the performance can be quite different as well. But like you say, the edge couplers at the moment don't show a clear benefit over the grating couplers. except for the grating couplers are a specific wavelength.
Yeah. And then I think overall the biggest challenge to both of these technologies is how you do the packaging and the alignment of all the components. And so if you have a solution that works with the grating couplers, I mean, it would be a completely different solution for edge coupling. And so in that sense,
yes,
it's a big investment. I think that's the hardest part of the problem is how to connect all the pieces together. So
yeah, I mean, in most of our things we use. MEMS technology is what we tend to use for a lot of our alignments. And our MEMS technology is quite mature in the sense that we use it on lots of different products in different ways as well. And whether it's from laser to PLC, for example, or PLC to another platform like the Silicon Photonics, for example.
And when you say MEMS technology, do you mean like is it actual mechanical, electrical systems where things are moving, or is this more of a flip chip bonding technology?
It's maybe MEMS is not the best word. Perhaps micro machined technology without the electronics.
Okay. Okay, so using things like balls and V-grooves and other kind of mechanical snapping features to align objects.
A lot of the Kaiam presentations, I can probably send out some videos on this as well. We've got a lot of information that's available online as well, but I tried not to include that in this presentation just to keep it focused on Silicon Photonics. But in fact, probably one of the things that Kaiam would count as one of its superpowers really is its micro-machined technology, or its MEMS technology. So it's quite easy to send a link that the folk on the course also can just watch the video and see how it works and what it does. This would be alignment between the laser and the PLC, so it's a different product, but it'd be quite interesting to see how the MEMS is used for that. Again, I use the word MEMS here maybe a bit more loosely than its exact definition.
Okay, so if anybody wants to follow up, who's watching this with you afterwards, I guess you shared with us your LinkedIn profile, so probably that might be the easiest way for somebody to get in touch with you. Is that?
Yeah, of course, yeah. I'm quite active and proactive on LinkedIn, so it's good to kind of, it's a small optics community, so it's great to get to know the people out there and share ideas. Yeah, please do.
Great. Well, it's very impressive what you guys have accomplished. It's beautiful to see. So how many, actually, just out of curiosity, how many people were involved in this design?
Oh, in this specific, the transceiver itself, the design side of it. So the Silicon Photonics in the transceiver or the transceiver?
Whichever way. I mean, you could break it down. How many Silicon
Photonics would be a couple of people, maybe 2-3 people.
Okay.
But if it's but that's from Kaiam's side. I'm not entirely sure of how many were involved from the partner side. But at the transceiver itself, there'd be lots of people on the team because the transceiver, like you say, there's the package inside, there's RF, there's lasers, there are MEMS, there are mechanical. There's so many engineers and skills that are involved in it. So there's, you'd say maybe at least 5 principal engineers of different disciplines with their engineers in it. So you've got our designers in it. So you've got probably about on different times 10, 15 people that are involved at different stages of a project as well. And that's including as well perhaps bringing it up to a manufacturable level as well. So it's not just prototyping. Yeah, I mean, there's. I think that's one of the exciting things about what we do, I guess, as well. It's not just one item. It's lots of different engineering disciplines coming together to make something, which is quite cool, I think.
Yep. No, it's fantastic. All right. Well, thank you very much, Ramsey. Appreciate your time. Thanks for sharing with us what you're doing, and best of luck.
Yeah, thank you very much. And I'll try to send you some more information on the different. So you can add to the comments later on.
Sounds great. Thanks, Ramsey. Bye-bye.
Thank you very much. Okay, bye-bye.
Bye-bye.